Okay, this is chapter 19.5 on page 371 in your OCRA physics book. There are three types of spectra. You've got emission line spectra, continuous spectra, absorption line spectra. The emission line spectra is where each element produces a unique emission line spectrum because of its unique sets of energy levels. Continuous spectra is where all visible frequencies or wavelengths are present. The atoms of a heated solid metal, for example lamp filament, will produce this type of spectrum. Absorption line spectra is where it has a series of dark spectral lines against the background of a continuous spectrum. The dark lines have exactly the same wavelength as the bright emission spectral lines for the same gas atoms. For today's lesson, we're going to be talking about some key terms that's used in cosmology or astrophysics. Okay, so homogeneous means that the matter in the universe is evenly distributed. Okay, or evenly spread out. Isotropic. Isotropic means that the directions are all the same no matter where you are. So let's just say that you're in the middle and you're looking in all directions. It's the same. It's the same in all directions. That implies that there is no center, no edge. The first one implies that it is smooth on large scales. Okay, and then number three, the laws of physics are the same. The laws of physics are the same. So these are cosmological principles. Now we're going to be talking about Wien's displacement law and Stefan's law. The equation for this is that the wavelength is inversely proportional to the temperature. So the higher the temperature, the lower the wavelength. For example, if something is cool but still hot, it will be red. As you increase the temperature, it becomes yellow, white, and then blue, bluish. Now the blue comes from ultraviolet, but we just see that blue part of the ultraviolet. So you start off with red, orange, yellow, white, and then blue, because that's from ultraviolet. So what happens when we substitute this proportional sign into a constant? So lambda is equal to some constant divided by t. So this constant is equal to lambda times t. This constant you're given in the data booklet, but you're not expected to know this constant. You're also given this graph in the book. So this is wavelength. This is wavelength for lambda, and this is I for intensity. So I for intensity, lambda for wavelength. Now this is a graph for temperatures. As you increase the temperature, the peak wavelength gets shorter. So here is the peak wavelength, here is the peak wavelength, and here is the peak wavelength. So this top graph is when the temperature is very hot. This bottom one here is when it is cold. As something gets hotter and hotter, the wavelength gets shorter and shorter, and the intensity gets higher and higher. That is Wien's displacement law. Now let's look at Stefan's law. Okay, let's talk about Stefan's law. That is incorrect because it's spelled with an F. Alright, so Stefan's law. What it says is that the power per area is proportional to the temperature to the power of 4. Now the actual equation is that the luminosity is equal to 4 pi r squared sigma, because that's the constant, and then times by T to the power of 4. So this is luminosity measured in watts. This is measured in meters because it's the radius. This is a constant. And T is temperature. Measured in Kelvin, and it is the surface temperature. Alright, so that's the equation for Stefan's law. The luminosity measured in watts is equal to 4 pi r squared, the surface area, times by constant, times by temperature to the power of 4. Now we can merge the previous equation. The previous equation was lambda is equal to the constant divided by T. Let's eliminate T and rearrange for T. So T is equal to K over lambda. If we substitute that into here, you get L is equal to 4 pi r squared sigma K to the power 4 divided by lambda to the power 4. And you can work out R. So let's rearrange for R. So R is equal to, so if you put 4 pi downstairs, this 4 pi downstairs, sigma also downstairs, but because you're dividing it by a fraction, you're multiplying it by lambda to the power 4, and you're dividing it by K to the power 4. So R is equal to L divided by 4 pi sigma. K to the 4 goes downstairs, and lambda to the power 4 goes upstairs, and it's square rooted. Okay, so that is Stefan's law. Now let's have a look at an exam question. Okay, so the middle part is not in the OCR syllabus, and I did say part C, but what I meant was part 3. Alright, let's see if we can answer this question. The Sun behaves as an approximate black body radiator with peak energy radiation occurring at a wavelength of 5.2 times 10 to the minus 7 meters. Show that the Sun has a surface temperature of about 6,000 Kelvin. This is 2 marks. Part 2, the radiation received from the Sun at the top of the atmosphere is 1.37 kilowatts per meter squared. Show the Sun's luminosity is about 4 times 10 to the 26 watts. Distance from the Sun to the Earth is 1.49 times 10 to the 11 meters. This is 2 marks. And the final 2 marks, hence calculate the radius of the Sun. This is an exciting question. Okay, so let's try that question. I'm just going to write the values on the board. So we know that lambda is equal to 5.7 times 10 to the minus 7. 5.2 times 10 to the minus 7. And you should be given the constant. You're not expected to know this. So the constant is equal to 2.9 times 10 to the minus 3 Kelvin. No, yeah, it's just 2.9 times 10 to the minus 3. And the units is mk. And we want to work out, well, what was the equation? The equation for Wiens displacement law is that lambda is equal to k over t, and we want to work out t, isn't it? So t is equal to k over lambda, and that is 2.9 times 10 to the minus 3, dividing it by 5.2 times 10 to the minus 7, and you should get okay, so that is what you should get. Okay, let's try part C, not part B for the moment, because part B is not in the OCR syllabus, but I'll do that later. But for now, let's just do part C. All right, so for part C, we have to find the radius of the sun. Calculate the radius of the sun. Now you're given the luminosity in the question is 4 times 10 to the 26. And we already know lambda. Sigma and k are just constants. So, and what was k? So k is equal to this. And what is sigma? I think it was 5.67 times, hold on, let me find out what it is first. Ten to the minus 8. Right, so I left this equation here. So we're going to put all these values inside here. So you should get 4 times 10 to the 26 times lambda is that. Oh, 4. And this is 4 times pi times sigma is this. And k to the power 4. And this is all square rooted. All right, so let's put the numbers in. Okay, so it's the square root of you should get 7.62 times 10 to the 8 meters. All right, so let's do part 2, but first let's just cover a bit of theory. So we're talking about stellar flux. This is symbol for F, so symbol F. And F is equal to luminosity divided by 4 pi d squared. So let's just say that this is the star, and you're here. The star is emitting light. So the stellar flux is how much this light is emitting as it goes from the star to that point, as it spreads out, because it's spreading out over the surface area. So it is expanding. If you think about the light, is expanding as it's going from there to there, and this is this D here. All right, so this F is measured, well, this is measured as power over area. And in the question, you're given that F is equal to 1.37 times 1000 watts per meter squared. You're given D as 1.49 times 10 to the 11 meters. Okay, so we want to work out L. The question is work out L. So L is equal to F times 4 pi d squared. So that is equal to 1.37 times 1000 times 4 times pi times 1.49 times 10 to the 11 squared. So let's get a calculator out. It is 1.37 times 1000 times 4 times pi times brackets 1.49 times 10 to the 11 close brackets squared. You get 3.82 times 10 to the 26. And that is roughly equal to 4 times 10 to the 26.